go to equilibrium.
Yep.
You guys tell me which two are on there we haven't learned about yet.
C, D, C, A, B.
It might be three. Might be three of them.
We've talked about all these. These are just for pHs and
Yeah.
Ks.
Oh, it's
Constant.
fine, it's fine.
Maybe it's not under.
No.
I really wish I had mine somewhere, but I have no idea where it is.
N equals N.
Yeah, that one. What's that one?
N equals little m over big N.
No.
Where do you see that?
E
That's just-
equals m over v.
That's just.
Yes.
Yes.
I is equal to Q over Q.
Yeah,
Oh.
where's that?
Q over t. It's under
They
the,
have an
yeah,
electrochem.
it's the last page. No, yeah, last page.
That's me.
Hello. I do. Well, I'm inclined to let her go, but she's probably missing a class that doesn't really matter, like English or something.
Really?
All right,
Oh,
no,
boy.
just kidding. Yeah, she'll be done. All right, that's fine. I think she was a little bit like, is he serious?
You sounded serious.
Yeah, you did.
All right, that was, I recorded that too, so that's fine. Yeah, thermodynamics, electrochem. Sorry, I said equilibrium, I misspoke. Thermodynamics, electrochem, you have, delta G equals negative N F E naught, and then I equals Q over T. Those are the only two on here, I believe, we have not learned or talked about.
Yeah.
If you look at, the constants or the symbols, bless you, over on the right there, what's little n there, lowercase n?
Number of moles.
Moles. What's
That.
F? Faraday's constant, 96,485 coulombs per mole of electrons. And we'll talk more about that. And then E naught, standard reduction potential, which is a number you would have to be given. Now, for some reason, the AP decided to take the standard reduction potential chart off of your equation sheet. So there used to be another sheet on here that gave you all those reduction potentials. So I'm going to teach the same way, but if it's a problem where you need those, they have to give it to you. It's kind of like the heat of formations and stuff like that. You don't know them, so they would have to provide them. So we'll get into that. And then the one underneath it, I equals Q over T. What's I?
Current.
Current, in amps. So this is like electricity, obviously, which is what electrochem is all about. And then Q, charge in coulombs, and then T, time. So that we're going to be using for questions that are like, okay, you have a cell that's hooked up for 20 minutes. Calculate the current, and that would be the I. So we'll get into that. But those are the only two like kind of new things, and we'll get to those. Physics people,
Excellent.
and didn't you take it?
Yeah, I took it.
Yeah. You took it. Yeah. So Faraday's constant, you guys talked about that, right? A little bit,
Yeah,
current, right? Amps versus coulombs, right?
Yeah.
Okay, all right. So we'll get into all that. Now, I think what we'll do is review a voltaic cell, and then we'll get into the reduction potentials, and hopefully by the end of next period we can get into that negative NFE equation. Delta G equals that one, yeah. All right, here we go. And we will need the book, but not yet. All right, here's galvanic cell or voltaic cell. We'll start with this. So first of all, this is spontaneous, but what's the real way we say it now? Thermodynamically favorable. This is a battery. Okay, essentially these are batteries. And again, thermo.
What did that say?
This one, batteries.
No.
Spontaneous.
Nope.
Galvanic cell.
Galvin.
Like Galvanic. Galvanic cell. Spontaneous, thermodynamically favorable. And again, that is in the forward direction. Rechargeable batteries, it's when you give it electricity and it goes the other way. It goes in reverse. We'll talk about that. These produce electricity. Produce electricity from chemical reactions. So any battery in the world, the reason it's producing electricity is because the chemicals are reacting with each other, transferring electrons, and that creates a movement of, the electron movement creates electricity. And again, this equation, which we'll talk about next week, the coulombs, which is charge, and the current are related. So, anyways, we'll come back to that. But, so this is kind of review from Regents. What I'm going to do is give you a reaction. We're going to draw a cell, make sure we understand the parts of the cell, and then we'll get into, I'll have you get the books and we'll get into a little bit more complicated stuff. All right, so let's say we have, what's the reaction they have here? Okay, so they have, and actually let me back up. If you know a voltaic cell is thermodynamically favorable, what should the sign on delta G be? Negative. Good. So that's important. So that delta G equals negative NFE. If the cell is put together correctly and the concentration, everything works the way it's supposed to, that delta G will be negative. If it's positive, then the cell won't work. It's fine. It just won't work. So just keep that in mind. We'll come back to that. All right. Here we go. Here's the reaction. We have zinc solid plus CuSO4. When you write this in your notes, make sure you have space under it to draw a cell. AQ yields ZnSO4 plus Cu. This is pretty classic example. I'm not getting into any complicated balancing here. It's all 1 to 1 to 1. All right, let's draw a voltaic cell and make sure we know the parts. All right, so we got this thing here. We have a, this will be a voltmeter. And we got this thing here. And we got this thing here. This here is zinc. This here is copper. In here is ZnSO4AQ. In here is CuSO4AQ. In this thing, let's say, what did I put in there? KCl, AQ. All right. And that's good for now. Okay. So, if this was given to you, and they wanted you to label the parts, which would be a fantastic AP question, because it's easy once we review it. Can we label the parts? Well, what do I mean? Well, we have to know who's the anode, who's the cathode. We have to know which half cell, which beaker, is the oxidation half cell, which is reduction half cell. We have to know where the salt bridge is. We have to know what the salt bridge does. We have to know which electrode, the anode or cathode, gains mass, which one loses mass. Where are the electrons originating? Where are the electrons going? Right, so there's a lot we need to know and be able to label. And again, this is still kind of Regents level. Kind of. They still ask some of the same questions, which is good. So let's go through all of that, and then we'll get into the AP stuff, harder stuff. All right. So if you label all the oxidation numbers, this is 0, which is the same thing as this zinc bar, zinc 0. This is copper 0, that's 0. SO4 is -2, that's a spectator. That's just floating around in these solutions. No one really cares about that. Cu +2, zinc +2. All right. So if we were going to write the half reactions, so you can do it underneath, next to it, wherever you have room, we have our oxidation half reaction and our reduction. All right, so you should, hopefully, at this point, be able to just look at it and see who's losing, who's gaining. Right? Who's playing catch? Who's throwing it? Who's catching it? Right? Anybody want to throw it out there? Very similar to the one I had to do on the whiteboard. Yeah, Zn0 is being oxidized. Cu plus 2 is being reduced. So that means zinc is losing and copper is gaining. How many electrons are being transferred? 2. This is the exact same half reaction as the warm-up, except instead of H plus and 2 of them, it's just 1 Cu plus 2 yields Cu 0. I really stress in Regents the kids label the 0. They don't for some reason want to. Regents kids for some reason, maybe it was some of you just didn't label it, didn't want to, or forgot, or didn't think it was a big, I don't know. Here it's not actually as big a deal, but make sure you know it's a solid, right? So the ion is what's floating around in the solution. The solid is the actual electrode, right? Like the terminals on a battery. That's what those are. All right. So it's important to just know what's what. The ion is aqueous and the solid is solid. All right. So if you label the 0 or not, I'm not too worried about it as long as you understand it. So make sure you know who the solid is. What I'm getting at. All right. Good. So where's the salt bridge? KCl is the salt bridge. If you need to label it, label it. If you got it, then you don't have to. What's in the salt bridge?
Salt.
A salt. What's the difference between salt and a salt?
So many different salts.
Right. A salt is any ionic compound, metal, non-metal. Any ionic compound. There's a lot of those. What's salt and ACl? So this is a salt. Why? Because it's KCl. So what you have in here is it's almost like a slushy consistency, and it's jam-packed. And sometimes there's like these cotton plugs in them. So when you turn it upside, it's a U-tube. It's called, which is funny. So it looks like a U. You put the salt. I can show you. I have one. I just don't have salt in it. But when you turn it upside down and put it in the cells, you want the cotton to kind of absorb the solution so it doesn't come out. And then once it's in here, it'll essentially balance out, equilibrium basically, so it doesn't empty out, right? So anyways, you have K plus and you have Cl minus in there, a whole bunch of them. And what does the salt bridge do? All right. Well, what are these things? Wires. What flows through wires? Electricity, which is made of electrons. So the electrons are going through the wire. What's going through here? Ions. It allows ions to migrate. Does that ring a bell? Hopefully.
Yeah.
If you take the salt bridge out or remove one of the wires, it's the same thing. It breaks the circuit. So it's kind of a circuit. I know it doesn't really look that way, but without the ions transferring, these things can't do what they want to do. They can't lose gain electrons without ions moving. And without the wire, the electrons have nowhere to go. So, if I was going to label this with an arrow on the wire, what direction would we label the electron flow? From left to right or right to left? Left, right. So, left to right. This is giving electrons to this. So the electrons are flowing from zinc into the copper cathode. I just gave an answer by mistake. Right. So zinc this is our anode, and then this is our cathode. Anox red cat. The anode is oxidized and the cathode is reduced. How do you know that? Well, if you're given a reaction, or if they, I've been doing this long enough, you think I would know. I'm not entirely sure if they're going to give you a reaction, they're going to give you a picture. They'll give you enough information to figure out who the anode or cathode is. You just remember the little phrase, anox red cat. Okay? Anode is oxidized, cathode is reduced. So in this cell, there's oxidation going on. In this cell, there's reduction. So this is my oxidation half cell, this is my reduction. So this half reaction is actually what's going on in here. This half reaction is going on in here. Okay. The anode in a voltaic cell is negatively charged. So like a car battery, that's the black one. Okay. That's your negative terminal, and then the cathode is positive. Why is that important? And it says in my, I have like this cheat sheet of things that aren't tested anymore, but I don't always trust it. They say students will not have to label that. Okay, maybe they don't. But the reason I still teach it, one, it's part of this. Two, there's no bells, I'm sorry.
No bells.
We can stop. we can stop. There's no rush to do it right now. Take a few minutes here.